Hello, this will be a demonstration of proposition 2 from book 4 of Euclid's Elements, which requires us to, in a given circle, inscribe a triangle equiangular with a given triangle. The task to simply inscribe any triangle into a circle is trivially easy, but it is very helpful to inscribe a triangle into a circle that's equiangular with a given triangle. So that's what this proposition is all about. We begin by having a given circle, A, B, C, like so. We'll have A there. And we have just some given triangle. There's no restrictions on what exactly it can be. It can be scalene, it can be isosceles, it can be equilateral, it can be an acute angle triangle, it can be right, it can be obtuse, it doesn't matter, just any triangle. And our task is to inscribe a triangle into this circle, equiangular with the given triangle. Another thing to note, it's not always possible to inscribe a triangle equal to a given triangle. This area just isn't going to fit inside this thing. So that's why this is not part of the proposition. We begin by drawing at the point A the straight line GH tangent to the circle ABC. We did this by the porism of 316, which you're going to see used in this book as more of a construction rather than a statement of fact. It's tacit within the porism of 316 that this is how you construct straight lines tangent to a given point that's on the circle. 317 is about a point not on the circle. Porism of 316 is about a point on the circle. So that's how we do that. And next, at the point A, we construct two angles. We first construct the angle HAC, which is equal to the angle DEF. So that would look something like that. And then we make the angle GAB equal to the angle DFE, like that. And then we join the straight line BC. We construct the equal angles by proposition 123, and then we join the final straight line BC by postulate 1. Now, looking at this, we know that the angle HAC must equal its angle in the alternate segment. We know this by proposition 332. And so the angle HAC, which we know is equal to the angle DEF, is also equal to its angle in the alternate segment, in this case the angle ABC. So AHC is equal to the angle ABC. We also know that the angle HAC is equal to the angle DEF, so common notion 1 easily tells us that these two angles, ABC and DEF, are equal to each other. Similarly, we know that the angle GAB being equal to the angle DFE is also equal to its angle in the alternate segment, which is the angle BCA. That's proposition 332 again. And then we made the angle GAB such that it's equal to the angle DFE, and so common notion 1 again, the angle ACB is equal to the angle DFE. Now, moving on to proposition 132, we know that the interior angles of any triangle add up to two right angles, and so we know that the angle ABC plus ACB plus BAC must equal two right angles, because the figure ABC is a triangle. And we also know that the figure DEF being a triangle, its interior angles have to add up to two right angles. And that would mean that the angle DEF plus DFE plus EDF equals two right angles. And we have two things which are equal to the same thing, namely two right angles. So these two things, again by common notion 1, are equal to each other. So we can say that the angle ABC plus ACB plus BAC is equal to the angle DEF plus DFE plus EDF. Now we have equals here that we can subtract from these equals so that we get equal remainders. In this case, we know that the angle ABC is equal to the angle DEF. We showed that to be true. And similarly, we also showed that the angle ACB is equal to the angle DFE. And so by common notion 3, if we subtract these equals from equals, the remainders will also be equal. What that means for us here is that the angle BAC is equal to the angle EDF. Right, so now we have that. And what we have here is the triangle ABC, which is inscribed into the circle ABC, such that it is equiangular to the given triangle DEF. Now, this being what was required to have been proven, or required to have been done, we are done with the proposition QEF. I have nothing to add to this proposition, so I'll simply move on to proposition 4.3.